Hello and welcome to Updegree. This is Sujay, your instructor for the OpenCV practical course. In this video, I'm going to cover the course curriculum that we will be covering in this course of OpenCV practical course. So the objective of the video is to go through each of the topic that is planned for this course and try to see why we have selected this topic and what is the advantage of learning this particular topic in OpenCV and how it will be useful for developing applications in OpenCV itself. So that would be the objective of this video, where as you can see from the screen, we have listed down each of the topic that we will be covering during the course of this video, and we will go through each of them trying to see why we need that topic and what can we learn in that topic so that it will become useful for us when we become experts in each of this topic. So now that we've decided that we are going to start learning OpenCV, next what we have to decide is what tools are we going to use for our craft. So tools help us practice our craft, but they do not make us a good craftsman. So a good craftsman will have many different tools in his pocket, but he judiciously uses the one that is most appropriate for the job. So it's not that she is married to the tools, but he is married to the craft. So that is why for OpenCV we have a many number of tools available for us in order to execute our projects. So some of these tools available to us are C++, Python and Matlab. Often there are a lot of wars going on between programmers over programming languages. They have very strong opinions about which programming language is better, and the truth is that the programmer should just choose the language that is appropriate for their task. In computer vision we have a lot of choices. So which tool should a computer vision engineer or a programmer learn? OpenCV using C++, OpenCV using Python or Matlab? The good news is that today we have a few options to choose from. A decade back there were no good libraries for computer vision. If you wanted to learn, you just picked a book and started coding your own mini library of computer vision algorithms. Thankfully, things are much better now. If you are a beginner, I would suggest using the path of least resistance and picking a tool you are familiar with. If you are already a Python programmer, use OpenCV with Python. If you are not familiar with Python, then it's better to learn Python and then pick up OpenCV with Python. But if you are already very good at C++, use C++ with OpenCV. Similarly, if you are already good in Matlab, use Matlab. That said, in a few months you will no longer be a beginner and you may be looking to apply this newly acquired knowledge to the real world. You could be thinking of a new side project or looking for a new job in this area. It pays sometimes to know how to make your choices. So in this video we'll be going over some of the pros and cons of each of the three tools that are available to us for OpenCV. So first one is the Matlab for computer vision. So until recently, computer vision was a research area in its infancy. People who worked in computer vision were mostly in the academia or research labs. Their tool of choice was Matlab, and for the longest time OpenCV was nowhere in comparison to what Matlab and its community had to offer. In the last 7 years the tide have turned, and here are some of the pros of using Matlab. Why should you use Matlab for computer vision? So the number one pro is the powerful matrix library. Not only do we treat an image as a multidimensional matrix in computer vision, we use a heavy dose of linear algebra also in various algorithms. Matlab's linear algebra routines are very powerful and blazingly fast. Once we needed to solve a large sparse linear system as part of an algorithm, and it was just a one-line code in Matlab. Whereas in C++ it would be at least 3 times faster than the Matlab implementation. It took us days to match the performance of the Matlab routine, and so in Matlab a single operator is sometimes a collection of powerful algorithms that Matlab appropriately chooses for you. The second pro is the toolboxes. Whatever your needs, there is a toolbox for that. They have an image processing toolbox, a computer vision toolbox, and a statistical and machine learning one that provide implementations of a wide variety of very useful algorithms. The functions usually provide a clean and obvious interface. Many computer vision problems are often set up as optimization problems. You are trying to maximize or minimize some objective functions under certain constraints. The optimization toolbox in Matlab provides excellent implementations of many optimization algorithms. The next pro is the visualization and debugging tools. One of the joys of using Matlab is that writing code, visualizing results, and debugging happens in one integrated environment, and that environment makes you extremely productive. The next pro is that it also works with OpenCV. So even though Matlab has its own computer vision programs, we can also interface it with OpenCV. The next pro is that it has great documentation. Even staunch supporters of OpenCV admit that the documentation is not as good as Matlab's. Matlab comes with great documentation and examples that are easily accessible within the IDE. Great documentation alone can make coding in Matlab 2 times faster. Matlab functions are also better designed compared to other libraries. And they also have a large research community because they are extremely popular in the academia. Latest research demos are often shared as Matlab code. If you want to be on the cutting edge, you should be able to read Matlab code. Coming to the cons of Matlab. So the number one con of Matlab is that the cost is huge. Matlab is hideously expensive. Let us start with the basic Matlab, which is like $2,150, and throw in the computer vision toolbox, which is $1,300. But the computer vision toolbox requires the image processing toolbox, which is another $1,000. Add optimization and machine learning toolboxes, and that brings your grand total to $6,850. So now that you have built your application and want to deploy it, well, you gotta buy the Matlab compiler, which is another $4,250. And if you want in 2 different operating systems, that would be another $4,000. So this Matlab makes sense only if you get it for a discounted price through your university or if your company already has a license. Otherwise, it is very, very expensive. The second con is the learning curve. The learning curve of Matlab is very, very steep. Matlab is a matrix engine. There is a Matlab way to write code which is different from the general purpose programming language like C++ or Python. And if you do not write code the Matlab way, your code can be extremely slow. Coming to the third con, it has a slower runtime. A typical Matlab program runs many times slower than a C++ program. Built-in Matlab routines can be very fast, but the code you write in Matlab will usually run much slower. Oftentimes, people end up coding computationally intensive parts in C and integrating it with Matlab code using mechs. So these are the pros and cons of using Matlab. Now that we saw the pros and cons of Matlab, now let us look at the pros and cons of OpenCV for C++. So why should you use OpenCV for C++ for computer vision? So the number one pro is that it is free. Large parts of OpenCV for C++ are free. That is free as in free speech. You can use OpenCV for C++ freely in your commercial application, and you can also view the source and fix issues if needed. You do not have to open source your project if you use OpenCV for C++. The second pro of OpenCV for C++ is that it has a huge optimized library. The collection of algorithms available in OpenCV for C++ dwarfs everything out there. The library is also optimized for performance. With OpenCV 3, you can use the transparent API to easily use OpenCL compliant devices, that is, GPUs on your machine. Many algorithms also have a CUDA implementation. This allows you to use the GPU in your machine to have fast compute. The third pro is the platforms and devices. You can obviously use OpenCV in your desktop app or as the backend of your web application. Because of its focus on performance, OpenCV for C++ is the vision library of choice in many embedded vision applications and mobile apps. The fourth pro is the big community. There is a big community of developers, 47,000, that use and support OpenCV. It has been downloaded more than 9 million times. Unlike the Matlab community that consists of researchers, the OpenCV community is a mix of people from many fields and industries. The OpenCV development is funded by companies like Intel, AMD and Google. Needless to say, This video is part of this vibrant community of people who are trying to help each other out. But regarding all of these pros, there are also some of the cons of using OpenCV for C++. So the number one con for OpenCV for C++ is that it is very difficult for beginners. If you do not already have considerable programming experience in C++, using the OpenCV C++ will be very daunting and very scary. You are probably better off trying to use Python instead of C++. The second con is that it has very weak documentation. OpenCV for C++ documentation is bad. Sometimes you need to have a good understanding of the algorithm and actually read the paper, because the documentation does not always explain what the parameters mean and how they affect the outcome. The documentation does not always come with sample code, and that makes it harder to understand. The sample code that comes with OpenCV, though very useful, is also not very well documented either. Let's just say that this is still a work in progress and people are chipping in to make it better. The next con is that it is a very small machine learning library. A computer vision engineer frequently needs many machine learning routines. OpenCV has a small set of machine learning algorithms compared to the choices available when you are using Python for OpenCV. The next con is the visualization and debugging. The debugging and visualizing is hard in any C++ environment. This is especially true if you are coming up with a new algorithm from scratch. Occasionally, people dump data to disk and analyze it using Matlab, because the visualization and debugging support in C++ is very less. So these are some of the cons of using C++. Although these cons might seem very big and that you will never use C++, but the pros outweighs the cons once you go to higher level. Once you are familiar with OpenCV and you want to deploy it in a commercial project, latency and optimization becomes very important rather than visualization and debugging and documentation. So in those scenarios, you will obviously opt for C++ because you will need a very fast and optimized library for implementing your computer vision algorithms. Therefore, even though right now C++ might not seem like a good candidate for us, we will be using C++ later once all of us become familiar with OpenCV and we have no issues with OpenCV's internal algorithms, and the only issue becomes C++. Now coming to Python. So Python is the next default choice for OpenCV. So why Python? Some of the pros and cons we will explore in this video. So I believe Python bindings for OpenCV have contributed quite a bit to its popularity. It is an excellent choice for learning computer vision, and it is good enough for a wide variety of real-world applications. Let's look at some of the pros and cons why you should use OpenCV for Python for computer vision. The number one pro is the ease of use. If you are already a Python programmer, using OpenCV for Python would be very easy. Even if you are not a Python programmer and you are very new to programming, Python is a very easy language to learn, especially when compared to C++. It is an excellent first language to learn. So that is why it has very good ease of use. The second pro of OpenCV for Python is that Python has become the language of scientific computing. A few years back, Matlab was called the language of scientific computing. But now, with OpenCV, NumPy, SciPy, scikit-learn and Matplotlib, Python provides a powerful environment for learning and experimenting with computer vision and machine learning. The third pro is the visualization and debugging. Although visualization and debugging was very hard in C++, when using OpenCV for Python, we have access to a huge number of libraries that are written for Python. Visualization using Matplotlib is about as good as Matlab, and also debugging code in Python is much easier than in C++. Although it does not reach the easierness of Matlab, Python is almost there. The next pro of using Python is that Python is used for building web backend. Python is a very popular language for building websites. Frameworks like Django and Flask allow you to quickly put together web apps. It is very easy to use OpenCV for Python along with these web frameworks. So most of the computer vision algorithms that we will be writing will be exposed through web backend. Therefore, if your web backend is also written in Python, it becomes very easy for us to export our OpenCV algorithms that we have written using Python and expose them using this web backend. Although these pros are very nice, there are also some cons associated with Python. The number one con is the weak documentation. As we mentioned before, OpenCV for C++ documentation is not very good, but the Python documentation is even worse. A novice user is left guessing how to use certain functions. The next con is the lack of support. Companies that support OpenCV like Intel, AMD, Nvidia, etc. have a dog in the fight when it comes to the C++ version of OpenCV. They want you to use OpenCV and to buy their hardware, which are CPUs and GPUs, to run these algorithms. But OpenCV for Python seems to be the proverbial red-headed stepchild that does not seem to get their attention. The next con is the slower runtime. Compared to C++, your programs in Python will typically run very slow. To add an extra punch, you can use the GPU using CUDA or OpenCL in OpenCV for C++ and have code that runs 10 times faster than the Python implementation. The last but not the least con is that OpenCV is written in C++. One of the great benefits of an open source library is your ability to modify them to suit your needs. If you want to modify OpenCV, you have to modify the C++. So, to summarize, as engineers, we need to use the right tool for the right job. Eventually, we will have to learn all the tools in this trade. As a rule of thumb, we will be using OpenCV for Python for prototyping new algorithms, and we will be using OpenCV C++ in production. Therefore, for this course, we will be starting OpenCV using Python because that is the easiest language for us to quickly prototype new algorithms and learn the algorithms that are present in OpenCV. Once we are familiar with the algorithms and we are familiar with using them, then we can shift to C++ in order to write efficient and fast code that can be deployed in production.
Hello and welcome to Updegree. This is Sujay, your instructor for the OpenCV practical course, and in the previous videos we went through the introduction and the course curriculum that we will be covering in this course, and I think it is time for us to start. So coming to the main question, what is OpenCV? So OpenCV is a library of programming functions modules that are mainly aimed at real-time computer vision. So what exactly is computer vision? So computer vision is that domain of computer science which mainly deals with images and videos that correspond to our sight. So we see our world in the form of a video and we process them in the form of images. So processing of these images and videos by a computer is called as computer vision. So this OpenCV as a project was originally developed by Intel, and later it was supported by Willow Garage, then ITSEs, which was again later acquired by Intel. So this library is a cross-platform library and it is free for use under the open source BSD license. So what does it mean by the word cross-platform? Cross-platform means that OpenCV can be run on many platforms, including different types of CPU architectures and different OSs. So for example, the OpenCV can be run on Windows, Mac OS, Linux, FreeBSD, Unix, and all sorts of operating systems, and it can also run on 32-bit and 64-bit architectures. So that is why this library is called as a cross-platform library, and it is an open source software. So what does open source mean? So open source means that we have access to the source code, and if we want to change the OpenCV or add new features to OpenCV, we can just download the source code and make changes to it as we see fit. So that is why it is called as an open source with a BSD license. Now OpenCV also supports deep learning frameworks that are in vogue right now, such as TensorFlow, Torch, PyTorch and Caffe. So officially OpenCV was launched in 1999. It was initially an Intel research initiative to advance CPU intensive applications. So it was part of a series of projects including ray tracing and 3D displays. So the main contributors to the project included a number of optimization experts from Russia, as well as Intel's own performance library team. In the early days of OpenCV, the goals of the project were described as advance vision research by providing not only open but also optimized code for basic vision infrastructure. So basically, for all the basic vision or image and video processing, the main objective was to build an open sourced optimized code that can run in real time. So a decade ago, what used to happen was, if you wanted to write a simple computer vision application, you had to reinvent the wheel, sit down and write all the algorithms, everything by yourself. But the vision of this project was that you don't have to write everything by yourself. Most of the algorithms are pretty standard algorithms, and once you implement them, you can just reuse these modules instead of you sitting and writing your own modules. Thus, there is no more reinventing of the wheel. The second vision of this project was to disseminate vision knowledge by providing a common infrastructure that developers could build on, so that there is a common infrastructure that everyone can see where the project is heading and can contribute in whatever way they can. So the code is more readily readable and it is transferable, so everyone knows what is happening inside the code and they can easily start contributing to the code and make it better and better. So this is one of the interesting aspects of any open source software. When you make an open source software, developers from all over the world come in and they can contribute their code to the software, and this not only keeps the software open, it also keeps it free of bugs and free of security concerns, because the software is open. And also because everyone around the world is adding features to this software will contain most of the algorithms that we would ever need for any computer vision problem. So the other vision of this was the advanced vision-based commercial applications by making portable performance optimized code available for free. So this means that making OpenCV itself open and optimized to run fast means that other people can use this code to build their own commercial applications and make the world a better place. So the first alpha version of OpenCV was released to the public at IEEE conference on computer vision and pattern recognition in 2000, and 5 betas were released between 2001 and 2005. So the second major release of OpenCV was in October 2009. So OpenCV 2 includes major changes to the C++ interface. So one important thing to note that is that OpenCV is written in C++ and its primary interface is in C++. So what does this mean? That means OpenCV itself, that is the core software, is written in the C++ language. One of the main reasons being that C++ is a very fast language and has very slow runtime. That means code written in C++ runs very fast, and this is especially useful because we will be building real-time computer vision applications, and for that we need blazingly fast processing. That's why OpenCV is written in C++. Now, even though OpenCV is written in C++, it has multiple interfaces. That means these interfaces can be used by other languages to provide support in other languages. That means the interfaces of C++, which is written in C++, can be implemented in Python, enabling us to use OpenCV in Python also. So this makes it a very versatile module, and therefore we will be using OpenCV in Python. So applications of OpenCV areas include augmented reality, motion tracking, structure from motion, stereopsis, segmentation and recognition, object identification, motion understanding, mobile robotics, human-computer interaction, gesture recognition, facial recognition systems, and so on and so forth. So OpenCV's applications, as you can see, is widespread, and it is used in almost all of the computer vision related software. So to support some of these areas, OpenCV's had to include a lot of machine learning libraries that contain many algorithms such as k-nearest neighbors, deep neural networks, random forest, naive Bayes, and decision trees. Now, although these are the main forte of machine learning algorithms, most of these algorithms are required in computer vision problems. Hence, the decision to include all of this in OpenCV. One of the important features of OpenCV that made it so powerful is that there are bindings in Python, Java, and Matlab or Octave programming languages. Therefore, it's not necessary for you to learn C++ in order to start using OpenCV in order to build your own applications. This has enabled a lot of developers who even though they do not know C++, they have used other languages such as Python, Java, JavaScript, and Matlab in order to build their applications. This has made this OpenCV a very popular framework indeed. Now, one more reason for this framework to be very popular is the fact that this can run even on Android and other mobile applications. So what this enables us to do is this enables us to build applications that can run on mobile phones, and as we can see in the real world, mobile phones are much more than computers, and having them perform computer vision applications is a very good advantage for us. Therefore, we have millions of developers across the world who are using OpenCV in order to build computer vision applications. So that's it for this video, and in the next video we will start getting our hands dirty, and we will start setting up the environment in which we are going to develop our sample applications in OpenCV.
Hello everyone, welcome to Updegree. This is Sujay and I am going to be your instructor for the OpenCV practical course. So in the previous video, we saw what OpenCV is, and we also saw the course curriculum for this course. So it's time to get our hands dirty and start setting up our environment. So I am going to be using Ubuntu as my base OS. I am going to be using Ubuntu 1.0 18.0 version, which is the latest Ubuntu release. So I hope all of you are also using the same Ubuntu so that we do not run into any issues regarding the OS or the versions, etc. It will be very easy for you to keep up with what I'm doing if you are also on the same OS as I am. So I am using Ubuntu 18.10 and I will be using the same thing for all my future applications. So the first thing that we need to install is called as Python. So as we already know, Python is a programming language that we are going to be working in, and we will be using that. So now all of you might be wondering, wait, Python is already installed, it's already built in Ubuntu, right? So why are we installing it again? So to do that, I would request all of you to open your terminal and type Python --version. As you can see, you might have a different Python version, but it will be 2.7 point something. So the thing is, Ubuntu comes something called as Python version called 2.7. Now this is the system Python version. So now what I'm going to teach you is to install something called as virtual environment, so we do not get into issues such as versioning issues, which I will be explaining in a very short while. Now coming to why I said we will be installing Python on our own is because of this. So let me give you a brief idea about why I said that. So basically, let us consider that this entire thing is our Ubuntu system, and Ubuntu has its own Python. This is the system Python. So this is the system Python that we get to see in the terminal when we do Python --version. So if we go to our terminal and we do Python hyphen version, it shows that it's Python 2.7.15. So Python 2.7.15 is the system version, which is this. Now we will be doing a lot of stuff in the Python, and therefore we do not want to touch this system Python. So this system Python will be getting used by a lot of other repositories inside Python itself, also inside Ubuntu itself. Ubuntu has a lot of other modules that might be dependent on this system Python. So therefore what we do is, when we install a separate Python installation inside Ubuntu that is separate from the system Python. So how we do this is we use something called as PyEnv. PyEnv is a tool that we will use to install our own custom Python version. So in that case, whatever is, if this becomes a danger zone, if we break this custom Python somehow, this does not affect the system Python. So in that case, we will keep all the other dependencies safe, so that if we corrupt the system Python, then all the dependencies of Ubuntu will also get corrupted and your Ubuntu might break. So that is why we will install another custom Python installation that is separate from the system Python, so that we do not have any issues with later on if we break the Python version. So thank you for watching this video, and in the next video I will be walking through installation of different Python versions. Hello everyone, welcome to Updegree. This is Sujay and I will be your instructor for the Opencv practical course. Now I would like everyone to open this website called PyEnv. So here you can see the URL. So the URL is https://github.com github.com/PyEnv, which is PYENV/PYENV. So I will give you guys some time to open this website, which should look something like this. Alright, so now that you guys have opened this website, I would just like you to start reading what it is. So PyEnv lets you easily switch between multiple versions of Python. It's simple, unobtrusive, and follows the Unix tradition of single-purpose tools that do one thing well. So what does this mean? So this means that in this diagram that I drew, we can not only have our own custom Python version, we can also have different Python versions. So what does this mean? I can have a Python 2.7 installation here, I can have a Python 3.6 installation here, and they would be both separate. So let me do a cleaner illustration of what I meant. So if you have an Ubuntu, this is your Ubuntu installation, and this is your system Python, which is 2.7. Now what PyEnv lets you do is it lets you install multiple versions of Python, so that you can have a Python 2.7.14 or another Python version which is, let's say, 3.6.7, or another Python version, let's say 3.7.1. So all of these Python versions will be separate from each other and they will not interact with each other. So if you have a separate Python version, let's say Python 3.7.1, and you are using that to develop, and you break something in this does not affect this, or more importantly, the system Python. So therefore PyEnv gives you the ability to install and easily switch between multiple versions of Python. So how do we install this PyEnv? There are some things that PyEnv does that is important for us to go through. Firstly, PyEnv lets you change the global Python version on a per user basis. So this is called as the global Pythons. So the boxes that I have drawn here, since they all reside inside the Ubuntu system itself, they are all called as global Python versions. So what PyEnv lets you do is it lets you change the global Python version on a per user basis. It also provides support for per project Python versions. That means for each of the project that you build, you can have a separate Python version just for that project. It also allows you to override the Python version with an environment variable, and it also allows you to search commands for multiple versions of Python at a time. So this will be helpful in test across Python versions with docs. So usually whenever you write any program in Python, you want to make sure that it does not break when it runs with a different Python version. So therefore this tool is usually used for testing across Python versions. Now how do we install this? So let us go to installation. So in the installation, it gives us a lot of steps in order to install it. But there is another very easy installer that is written by a helpful user of PyEnv, which we can directly use to directly install in our system. So I would like you guys to go to this URL that can be seen in the video right here. So the URL is https://github.com/PYENV/PYENV-installer. Go ahead and open this website. Alright, so now that we have this website open, let us go down and see what this does. So this tool installs PyEnv and friends. So this is a very useful tool for us that makes our lives very simple. So there are some prerequisites. So one thing is it is important to go through each of this. So in general, compiling your own Python interpreter requires the installation of the appropriate libraries and packages. So the installation wiki provides a list of this for common operating systems. Since we are using Ubuntu, all of these prerequisites will already be in our systems, so we do not have to worry about this. Now what we have to do is we have to execute this command. So what this command tells us is curl this command and pipe it to bash. So we are going to get the file, that is this file, and then we are going to execute it using bash. So let's go ahead and do that. Now once you type this, press enter. I am not going to press enter because I have already installed it and this might cause me some trouble. But you should press enter and it will guide you through the installation process. So if all went according to plan, that is if the installation ran successfully, if you see the logs, you can see something along these lines. So in the end, it would have asked you to add these 3 lines to your .bashrc file. We have to add that to our .bashrc file. Now your .bashrc file will be in your home directory. So if you do a pwd, you should be in /home. So if you do a pwd, you should be in /home/username. Here I will be using Sublime editor. You can use anything such as Gedit or Vim or any other editor that you would like to use. So I will be using Sublime and I will open .bashrc file. Now once I have opened the bashrc file, you can see that the file will look something like this. Now go to the end of the file, scroll down all the way down and add these 3 lines that you saw in the terminal when you installed PyEnv. So once you've added the 3 lines to the bashrc file, save it and go back to the terminal and type source.bashrc. Now I am getting an error here because of another shell, but you should not be getting this error. So your source.bashrc should work without throwing any errors. Make sure that source.bashrc does not throw any errors for you before continuing further. So if your source.bashrc work perfectly fine, then it is time for us to test it out. Going back to the terminal, type PYENV versions. So when you type this, you should get something like this, only system. I am getting a lot of versions because I have already installed these versions. For you, it should contain only system. So as you can see, it shows that there is only a system version. I have installed other versions that are separate from system. So what I want you guys to do is install another Python installation. And how do we do that? Let us go back to our documentation. Let's go to installation. Here, as you scroll down, it shows you how to install a new version here. Here we are using PyEnv to install 2.7.8, but in our case, we will be installing Python version 3.6.8. So please type PyEnv install 3.6.8 and press enter. Now it is going to take a couple of minutes. Now if you were able to install it without any issues, let us now try to change our Python version. Now if you do Python -- version, it is in Python 2.7.15. Now since we just installed Python version 3.6.8, let us change our Python version. Now if I do Python global 3.6.8, it should be PyEnv global 3.6.8. Now Python's version should be changed. Now if we do Python -- version, Python is 3.6.8. Now if you just type Python, you are inside the Python interpreter and it says that you are running Python 3.6.8 version. So as you can see, we have successfully changed the version of the Python and kept it separate from the system Python. So in the next video, we will be covering how to install VENV and OpenCV for our projects. Hello everyone, welcome to Updegree and this is Sujay. I'll be your instructor for the OpenCV practical course. So in this video, we will be installing VENV and using it for our projects. So for all our projects, let us create our own folder by going to desktop and we'll create a folder called OpenCV_projects. Now let us go into OpenCV_projects. Now this is an empty directory and here we will create something called as a virtual environment. Now in the previous video, we already set up different versions of global Pythons. Now let us set up a virtual environment. Now what exactly are virtual environments? So virtual environments can be defined as this. So let us say we have a base Python installation that we are using for project 1, project 2 and project 3. Now if project 1 requires, let's say, a module 1 of version 0.9.1 and project 2 requires, so project 1 requires a model 1 of 0.9.1. So your base Python version will have module 1 of 0.9.1, but your project 2 requires the same module of 0.8.0. So there is a mismatch between the requirements of project 2 and project 1, because project 1 requires module 1 of a different version from the project 2, which requires a module of a different version. So now if you say that you are working on project 2 and you overwrite this and you make this, you overwrite this and instead install 1.8.0, your project 1 cannot use it. So as you can see, because of this versioning conflicts between projects, we use something called as virtual environments. So what does virtual environment do? So what virtual environment does is, let's say we have a base Python installation and we have different virtual environments. So you can call this virtual environment 1 and this as virtual environment 2. So we have two different virtual environments that has two separate modules but sharing the same Python. So in the previous case we had project 1 and project 2, which needed module 1 of version 0.9.1, and this project 2 needed module 1 of 0.8.0. Now what virtual environment does is we can install module 1 of version 0.9.1 here, and we can install this version here. So here module 1 will be 0.9.1 and here module 1 will be 0.8.0. Now these two virtual environments are separate from each other. So project 1 can happily use module 1 which has 0.9.1 without worrying that project 2 needs 0.8.0. Now project 2 can keep using its own virtual environment without worrying about other virtual environments. Now creation of these virtual environments is what we will do now. So now that we have navigated to our directory, the way to create a virtual environment is to use the command python3-m venv and give the name of our virtual environment. So I am going to give the name of Opencv _virtual _env. So what this does is this creates a new virtual environment called Opencv _virtual _env and press enter. Now if you do an ls, as you can see, we have created a new Opencv virtual environment. Now how do we activate this virtual environment? So let's do a source Opencv _virtual _env /bin/activate. So as you can see here, this shows that we are inside this virtual environment. So we are totally outside the other environments and we are safe. We have created another virtual environment here called as Opencv _virtual _env. We have created a new virtual environment. Now let us see what are the modules that are installed in this virtual environment. So if you just do a pip list, you can see that there are no other modules that are installed other than the default ones. That means it is an empty virtual environment. So now what we are going to do here is we are going to install Opencv inside this empty virtual environment. Now, in order to install Opencv, make sure that you are inside the virtual environment. So inside the virtual environment, let us first update the pip that it is asking us to do, which is pip install --upgrade pip. So now that is done, we have to do is pip install Opencv -Python. Now this will install all the dependencies such as NumPy and Opencv inside this virtual environment. Now if you do a pip list, we can see that it has installed Opencv and NumPy. So in our virtual environment, what has happened is we have installed Opencv and NumPy. Now to test that we have actually installed Opencv and that Opencv is working perfectly fine, go to your terminal and type Python. Make sure your virtual environment is active and type Python. Now do import cv2 and it should not throw you any error. This should be your output. This shows that your Opencv was installed properly. So now that we've installed Opencv, in the next video we will be starting with our first project. So that's it for this video, and if you face any issues, please go back and find out if you've missed any of the steps. Hello everyone, welcome to Updegree, and this is Sujay, your instructor for your Opencv practical course. In this video, we will be starting off with our first Opencv project, that is the motion detector application. So in this project, we will be building a motion detector application that basically detects any motion that occurs in our input video. So before we begin, we have already set up our environment. So let us go to our environment and see how we have set it up. So we will go to desktop and Opencv projects. So here we have already created a virtual environment called Opencv virtual environment. So let us activate that. So now with that we have activated our virtual environment, let us see what all applications or modules that are installed in this virtual application. So here we have installed NumPy, Opencv, pip and setup tools. So there is another package that we will be installing, so called imutils. So we have installed imutils. Alright, so now let us open our favorite text editor. I have created a new file called as motiondetection.py, and then we will save this in the folder that we created. So here I have saved it as motion_detection.py, and let us save it. So let us start importing some of the modules that we will be requiring. So now that we have imported all the modules that we need, now let us construct an argument parser and pass the arguments. So now let us save this file. So here what we are doing is we have imported the necessary packages that we will be needing in this section of the code. In this section we are importing something called as a video stream. So video stream is a package of imutils video that helps us to start streaming from our webcam. We are importing the argparse module so that we can read we can read the arguments given by the user from the argument line. And then we are also importing date time, because later we will be recording at what date the motion sensing algorithm was triggered. IMUtils is one of the helper modules that helps us read videos and images and work with them. Time and CV2 obviously is the CV2 is the OpenCV module that we will be importing to work with our application. So the first line, here we are initializing an argument parser that is going to parse the arguments given during runtime. So first we are going to add an argument called video. So if we give an argument called --video and path to the video file, we can read that video file. The second argument that we are sending is the min area. So min area size is the minimum area size that we will be looking into for the motion detection. So this will be of type int and it will be default of 500. So next we will find out the args, which parses the args using this argument parser. So here what we are doing is, if we do not send any video file as input, then we are going to start streaming from the webcam itself instead of reading from the video file. Else we will start reading from the video file that we have captured from the video, and we are also initializing the first frame. So this is the initial structure of our code which we are going to develop, and in the next video I will be talking about the basic theory behind how we are going to do object detection. What is the theory behind motion detection? So we are going to build this motion detection app using something called as background subtraction. So a little bit about background subtraction. Background subtraction is critical in many computer vision applications. We use it to count the number of cars passing through a toll booth. We use it to count the number of people walking in and out of a store. And we use it for motion detection. Before we get started coding in this post, let me say that there are many ways to perform motion detection, tracking and analysis in OpenCV. Some are very simple and others are very complicated. The two primary methods are forms of Gaussian mixture model based foreground and background segmentation. In newer versions of OpenCV, we have Bayesian probability based foreground and background segmentation. We can find this implementation in cv2.createBackgroundSubtractor GMG function. All of these methods are concerned with segmenting the background from the foreground, and they even provide mechanisms for us to discern between actual motion and just shadowing and small lighting changes. So why is this so important, and why do we care about pixels belonging to the foreground and what pixels are part of the background? Well, in motion detection, we tend to make the following assumption. The background of our video stream is largely static and unchanging over consecutive frames of a video. Therefore, if we can model the background, we monitor it for substantial changes. If there is a substantial change, we can detect it. This change normally corresponds to motion in our video. Now, obviously, in the real world, this assumption can easily fail. Due to shadowing, reflections, lighting conditions, and any other possible change in the environment, our background can look quite different in various frames of a video. And if the background appears to be different, it can throw our algorithms off. That's why the most successful background subtraction or foreground detection systems utilize fixed mounted cameras and in controlled lighting conditions. These methods, although they are very powerful, are also very computationally expensive. So it is best that we stick to simple approaches. In the rest of this video, we will be detailing the most basic motion detector and tracking system that we will be building. So in this code, we have seen that we have imported all the necessary packages. All of these should be pretty familiar, and we have already installed the IMUtils package. So next we have passed the command line arguments. We'll define two switches here. The first is the --video, which is optional. It simply defines a path to the pre-recorded video file that we can detect motion in. If you do not supply a path to a video file, then OpenCV will utilize your webcam to detect motion. We'll also define -min-area. which is the minimum size in pixels for a region of an image to be considered actual motion. As we'll discuss later, we'll often find small regions of an image that have changed substantially, likely due to noise or changes in lighting conditions. In reality, these small regions are not actual motion at all. So we'll define a minimum size of a region to combat and filter out these false positives. In the case that a video file path is not supplied, we'll grab a reference to the webcam, or else we'll grab a reference to the video object. If a video file is supplied, then we'll create a pointer to it. Lastly, we'll end this code snippet by defining a variable called first frame. So first frame stores the first frame of the video file or the webcam stream. So here we are making a very important assumption. The assumption is that the first frame of our video file will contain no motion and just background. Therefore, we can model the background of our video stream using only the first frame of the video. Obviously, we are making a pretty big assumption here, but again, our goal is to run this system on a very simple algorithm so that we don't get too complicated. So in the next video, we will be starting with the next snippet of the code of the motion detection app. Hello everyone and welcome to Updegree. This is Sujay, your instructor for the OpenCV practical course. So this is the third video in motion detection application, and in this video we'll be covering the next snippet of coding. So you can follow along as I start coding. So the call to vs.read returns a frame that we ensure we are grabbing properly. We'll also define a string named text and initialize it to indicate that the room we are monitoring is unoccupied. If there is indeed activity in the room, we can update this string. And in the case that a frame is not successfully read from the video file, we'll break from the loop. So in this case, we are reading the frames using vs.read, and we are assigning the frame depending on which source we are reading it from. If we are reading it from a video file, then we are assigning it as frame, or else we are assigning the first element of the frame array. And we are also initializing the text as to unoccupied. So if we are not able to read the file, then that means we have reached the end of the video and we are going to break from this while loop. Now we can start processing our frame and preparing it for motion analysis. First, we'll resize it down to have a width of 500 pixels. There is no need to process the large raw images straight from the video stream. So what we do here in the resize function is that we resize it to a width of 500. Usually our video files will have very large frame sizes and we don't have to pre-process all of them. And then we'll also convert the image to grayscale, since color has no bearing on our motion detection algorithm. Since our motion detection algorithm is based on background subtraction, we don't need a colored frame, we just need a black and white. Finally, we'll apply Gaussian blurring to smooth our images. So why are we doing this? So we do the Gaussian blur here in this line to apply a Gaussian blurring algorithm on our images. So why do we do this? It's important to understand that even consecutive frames of a video stream will not be identical. Due to tiny variations in the digital camera sensors, no two frames will be 100% the same even if there is no movement. Some pixels will most certainly have different intensity values. That said, we need to account for this and apply Gaussian smoothing to average pixel intensities across a 21x21 region. So here we are mentioning that we will be smoothing out the intensities across a square area of 21 pixels height and 21 pixels width. This helps smooth out high frequency noise that could throw our machine motion detection algorithm off. As I've already mentioned, we need to model the background of our image somehow. Again, we'll make the assumption that the first frame of the video stream contains no motion and is a good example of what our background looks like. If the first frame is not initialized, we'll store it for reference and continue on to processing the next frame of the video stream. The above frame satisfies the assumption that the first frame of the video is simply the static background. That means no motion is taking place. So up to here we have come to a point where we have the first frame which models our background and nobody is there in that video. And we have already pre-processed this frame and we know what a background looks like. So given this static background image, we are now ready to actually perform motion detection and tracking. So thank you for watching this video. This is the end of the third video, and in the next video we will actually start with the tracking algorithm that we discussed. Hello everyone, welcome to Updegree. This is Sujay, your instructor for the OpenCV practical course. In this video, we'll be going over the next snippet in the OpenCV practical application that is dealing with the motion detection application. So I will be starting to code and I would suggest all of you to keep up with me. Alright, if you have already caught up till here, let us continue. Alright, let us save this file. Now that we have our background modeled via the first frame variable, we can utilize it to compute the difference between the initial frame and the subsequent new frames from the video stream. Computing the difference between two frames is a simple subtraction where we take the absolute value of their corresponding pixel intensity differences. So here frame delta equal to background model minus current frame. So in this case we are computing the frame delta by computing an absolute difference between the first frame, which we have assumed to be the background, and the current frame, which is the gray. So the delta between these two frames is stored in frame delta. So the background of the image is clearly black, but regions that contain motion, such as region of movement, is much lighter. This implies that the larger frame delta indicate that the motion is taking place in the image. We will then threshold the frame delta to reveal regions of the image that only have significant changes in pixel intensity values. If delta is less than 25, we discard the pixel and set it to black. If the delta is greater than 25, we will set it to white. So in this case, we are thresholding on 25. So in this frame delta, if the intensity of the pixel is greater than 25, then we set it to 255, which is white. If it is less than 25, then we set it to 0. Given this thresholded image, it is simple to apply contour detection to find the outlines of these white regions. We will start looping over each of the contours, where we'll filter the small irrelevant contours. If the contour area is larger than our supplied min area, we'll draw the bounding box surrounding the foreground and motion region. We'll also update our text status string to indicate that the video has motion. So here we will find all the contours in this line. the contours of the image, of the black and white image, on the threshold frame. So in this line we are going to grab all the contours using the imutils module, and we are going to store all the contours in this variable. Next, we will loop over all the contours, trying to find out what is the area of each contour. Now, if the area of each contour is less than the minimum area that has been supplied in the arguments, then we are going to ignore it. Otherwise, we are going to get the bounding rectangle against the contour, which includes the x coordinate, y coordinate, the width and height of the rectangle. Now once we have this rectangle, we will initialize a new rectangle object over the current frame, and we also change the text to occupied. Better yet, we will change the text to motion is detected, and we will change the text here to no motion. And let us save the file. So here what we are doing is we are doing the absolute difference on the current frame and the previous frame, and we are doing a threshold on it. Only if the threshold is greater than 25, it is going to be considered as actual motion, because we don't want our motion detector to give false positives. Now this threshold can be tuned according to how our motion detector works. If this threshold is too low, we will increase it, and if the threshold is high, we will decrease it. This we will get to know once we actually run the application and test it. So after this, we do a dilation on it, which is a pre-processing step, and then we find contours on this frame. And then we loop over each frame trying to find the area of the contour, and only if the area is greater than the min area, we store that rectangle. So thank you for watching this video, and in the next video we will look into the next snippet of code where we will actually draw this contour on the frame and then change the text on the frame to whether motion is detected or motion is not detected. Hello everyone, and welcome to Updegree. This is Sujay, your instructor for the OpenCV practical course. In this video, we will start off with the next snippet of the motion detection app that we've been building. So in this video, we'll be going over how to actually put the text and the status on the frame itself. So as I code along, I would request you to start coding along with me and keep up with me. Alright, so let us save the file and continue on. Alright, let us save the file. So in this code snippet, we are just wrapping things up. We draw the status on the image in the top left corner, followed by a timestamp on the bottom left. So in these two parts, we are just displaying what is the status of the motion on the top left and the current datetime of when the motion was detected on the bottom part. So here we are just specifying the font, the opacity, the color, and where we have to put it. And then we are just showing the results of our motion detection using these three functions called IMShow, where we are showing the frame, the threshold that was used, and the delta. So, and then we are recording the key that is being pressed, so that if the Q key is pressed, we are going to stop the application. And after this, we are just cleaning up the camera and releasing any of the resources that we might be using, and we are destroying all the windows created by OpenCV itself. So now that we have done everything, the second part displays the results of the work and allows us to visualize if any motion was detected in our video, along with the frame delta and the thresholded image, so that we can debug our script. And in the final 2 lines, we are cleaning up and releasing the video stream pointer. So thank you for watching this video, and in the next video we will give this code a try and see how well it works. Hello everyone and welcome to Updegree. This is Sujay, your instructor for the OpenCV practical course. So till now we have coded our first motion detection application, and in this video we will be going through the demo and we will actually run it and see if actually our code is working. So for that, let us go to our terminal. So now let us type Python motion detection. So we will not be giving any arguments for the video file because we will be taking an input from the webcam. So here, as you can see, we have 3 windows. One is the frame delta, the threshold, and the frame. So here, as you can see, there is no motion right now. But if I introduce a motion, we can see that motion is detected. And you take out the motion and there is no motion. In threshold window, you can see that it is detecting the motion, that is the hand, which is different from the background. And in the frame delta, you can see the delta, that absolute difference that we have calculated. As you can see, the green line is the contour lines that are being drawn. So here, as you can see, the text is saying motion is detected, and you stop the motion and there is no motion, and you again introduce motion and it says motion is detected. So thank you for watching this video, and this will be the last video in the motion detection application, and see you in the next video where we will be building another application. Hello everyone, welcome to OpenCV practical course. This is Sujay, your instructor for the OpenCV practical course, and in this video we will be starting off with the second project in OpenCV, which is the hand detection application. We saw in the previous videos that we completed the motion detection application, in which we were detecting any motion given in a video. Now we will extend that idea of motion detection in order to detect hand in a video. So in the previous project, what we did was we took the background of a video and modeled how a background of the video looks like, and if the frame changes significantly from how the background looks like, then we were detecting it as motion. So similarly, even in this hand detection, let us see how we will be using similar principles of background modeling and thresholding in order to find out whether a hand or a gesture is being performed in the video. So in the next video, I will be going over some introductory concepts that are required for building a hand detection application. Hello everyone, welcome to Updegree. So this is Sujay, your instructor for the OpenCV practical course. In this video, we will be going over some basic concepts that we will be requiring for building a hand recognition project. So in the previous video, we saw a brief introduction to what hand recognition is, and in the previous video, we also built a basic motion detection application. So in this video, let me go through some of the basic concepts that are required for building a hand recognition software. So in this video, we will be going over some of the brief theory behind how a hand recognition project is built. So after this project, you will know how to approach a computer vision problem step by step. You will also know about background subtraction and motion detection, which we have already used and built a motion detection application in the previous project. Then we will also learn about what is thresholding, what are contours, so what is the difference between them, and how to build a contour and how to threshold an image. Then we will also learn how to implement the above concepts in code using OpenCV and Python. After that, we will also build an application which will segment hand region effectively from a real-time video sequence. Hand gesture recognition is a very cool project to start for a computer vision enthusiast, as it involves an intuitive step-by-step procedure which could easily be understood, so that you can go on to build more complex stuff on top of these concepts. So like I said before in the previous project, there are some prerequisites that we will need in order to go ahead. So I am assuming that you are already familiar with the basics of Python, NumPy and OpenCV, as they are the prerequisites for this tutorial. If you want to quickly understand core concepts in Python and NumPy, you can check out the basic documentations that are available online. In addition to these, you should also be familiar with image basics such as what are pixels, what is an image dimension, what is a video, what are frames of a video, frames per second, etc. and some basic operations with images such as thresholding and segmentation. Do not worry if you do not have an in-depth understanding about what all of these mean. If you know in a brief high-level view what these words mean, it is sufficient because we will be learning about them in this video. So coming to the introduction part, so gesture recognition has been a very interesting problem in computer vision community for a long time. This is particularly due to the fact that segmentation of foreground object from a cluttered background is a challenging problem in real time. The most obvious reason is because of the semantic gap involved when a human looks at an image and a computer looking at the same image. Humans can easily figure out what is in an image, but for a computer, images are just three-dimensional matrices. So for a computer, they are just RGB values of each pixel. If you are aware of what pixels and what RGB values are, you must already know that each image consists of pixels, which are individual dots in an image that make up an image. And each of these dots is represented by three values, that is red, green and blue, or RGB values. Now the values of these RGB is what determines its color. Therefore, for a computer, images are just three-dimensional matrices. It is because of this that computer vision problems remain a challenge. So another important challenge is the semantic segmentation problem, where the objective is to find different regions in an image and tag its corresponding labels. In a case of an image where there is a person, we will have to label which part of the image constitutes the sky and which part of the image constitutes person, which part of the image constitutes a tree and which part of the image constitutes grass. A quick Google search will give you the necessary links to learn more about these research topics. As this is a very difficult problem to solve, we will restrict our focus to nicely segment one foreground object from a live video sequence, which we are going to do in this project. So now, what exactly is the problem that we are trying to solve? So I will go ahead and let you know what is the problem statement. So the problem statement is that we are going to recognize hand gestures from a video sequence. To recognize these gestures from a live video sequence, we first need to take out the hand region alone, removing all the unwanted portions in the video sequence. After segmenting the hand region, we then count the fingers shown in the video sequence as a gesture. Thus, the entire problem could be solved using two simple steps. Find and segment the hand region from the video sequence, and 2. Draw a contour around the hand to segment the hand region in the video sequence. How are we going to achieve this? To understand hand and gesture recognition in depth, we have created this video for you to understand how to do this in a practical manner. So in the next video, we will start with the first part that we will need for this tutorial. So let's get started and see you in the next video. Hello everyone and welcome to Updegree. This is Sujay, your instructor for the practical OpenCV course. In this video, we will be going over the first part of building the hand recognition project, that is the second project in this video series. So in the previous video, we saw some of the prerequisites and the introduction that we had to go through before coming here. So let's get started. So the first part that we will need to do is we will need to segment the hand region. The first step in hand gesture recognition is obviously to find the hand region by eliminating all the other unwanted portions in the video sequence. This might seem to be frightening at first, but don't worry. It is a lot easier using Python and OpenCV. Now, I hope you all understand that a video sequence is just a collection of frames or a collection of images that run with respect to time. Before getting into further details, let us understand how could we possibly figure out the hand region. So the first part is the background subtraction. If you can see the slide, you can see that the first question that we will be answering is how to do background subtraction. So coming to this part about how to do background subtraction, first we need an efficient method to separate foreground from background. To do this, we use the concept of running averages. We make our system to look over a particular scene for 30 frames. During this period, we compute the running average over the current frame and the previous frame. By doing this, we essentially tell our system that the video sequence that you looked at, that is the running average of those 30 frames, is the background. After figuring out the background, we bring in our hand and make the system understand that our hand is a new entry into the background, which means that it becomes the foreground object. But how are we going to take out this foreground alone? The answer is background subtraction. So for all of those who followed the previous project, that is the motion detection application that we built in the previous video, then this must already be familiar to you guys. So even in the previous video, during the motion detection, we modeled the background by telling the computer that the first couple of frames is what a background looks like, and any changes to this background frame is the foreground. Now how did we do that? We recorded the video for the initial frames and we said this is how the background looks like. And after that, whenever motion was detected in that video, that means the background changed or a new object entered into the video, we detected it as the foreground. That means that the motion has been detected. So in the previous project, we just saw that as soon as the motion was detected, we put out an alert saying that motion was detected. But in this project, along with identifying when the motion has been detected, we also have to draw a bounding box and find out whether the foreground object that actually came out was the hand or was it just a random motion. So that is the challenge that we will be facing in this project. So like I explained, so background subtraction is done by taking an efficient method to separate foreground from background. So the running averages is something that we already established in the previous project, where we did not exactly a running average, we just took absolute differentiation or absolute difference between the background image and the current image, that is the frame of the video. So only if this absolute difference is greater than a threshold, we detected it as a motion. But in this case, we will be taking the running averages of 30 seconds. So what is running average? We will be calculating averages of the RGB values of the window over the frame. So after figuring out the background model using running averages, we use the current frame which holds the foreground object, which is a hand in our case, in addition to the background. We calculate the absolute difference between the background model, which will get updated over time, and the current frame which has our hand, to obtain a difference image that holds the newly added foreground image, which is our hand. This is what background subtraction is all about. So coming to the second topic, that is the motion detection. So as you can see in the slide, the second topic that we will be learning and doing is the motion detection part. To detect the hand region from this difference image, we need to threshold the difference image so that only our hand region becomes visible, and all the other unwanted regions are painted as black. This is what motion detection is all about. So you might be asking, what exactly is thresholding? So thresholding is the assignment of pixel intensities to zeros and ones based on a particular threshold level, so that our object of interest alone is captured from an image and everything else is marked with a 0. So you can consider this as kind of like a masking. So we will be masking all the pixels of the image that we are not interested with a 0, that means pitch black, and all the other regions that we are actually interested with white. So that is motion detection and thresholding. As you can see, the next topic that we will be covering is called as the contour extraction. So after thresholding the different images, we find contours in the resulting image. So the contour with the largest area is assumed to be our hand. So to summarize, what are the steps that we need to take is that background subtraction, motion detection and thresholding, and contour extraction. So we are already familiar with background subtraction and motion detection from the previous project. But this contour extraction is something that is new for us. So in the next video, I will be covering what exactly is contour extraction, and we will go from there.
Hello everyone and welcome to Updegree. This is Sujay, your instructor for the OpenCV practical course. In the previous video, we've learned about motion detection and background subtraction that we need to do in order to do hand gesture recognition. And we came to the third point of how to do contour extraction. So in this video, we will be going over some of the basic theories that we need to understand in order to do contour extraction. So what are contours actually? So contours in simply as a curve joining all the continuous points along the boundary having same color or intensity. The contours are a useful tool for shape analysis in object detection and recognition. In our case, since we are trying to build an object detection algorithm and the object being the hand, contours are very important for us to find out whether we are actually detecting a hand. So for better accuracy, before finding contours, we need to apply threshold or candidate detection. So in our case, we are already applying threshold. In OpenCV, finding contours is like finding white objects in black backgrounds. So we have to remember that the object background should be white and the foreground should be white. So like I said in the previous video, when we did thresholding, we applied black or 0 on the background and 1 or white for foreground. So now what exactly is contours? So to do contour detection, OpenCV provides a function called as find contours, which intends to find contours. Of course, some treatment should be applied to the picture in order to get good contour detection. So we will be first using threshold to subtract background from foreground. Then we should apply find contours function to find contours and print them in the color image. So there are some important points that we need to keep in mind while extracting contours. The image should first be converted into grayscale. A simple threshold must be applied. We should mask the background. The find contour functions is called with a list of contours, and these retrieved contours are applied colored. So now that we have understood what contours extraction is, let us go back and summarize what are the steps that we needed to follow in order to get the contours. So the first is the background subtraction, the second is the motion detection, and the third is the contour extraction. So now that we are thorough with the theory behind how to do the hand detection, in the next video I will be diving deep into code to explain how to do the code themselves.
Hello everyone and welcome to Updegree. This is Sujay, your instructor for the OpenCV practical course. In this video, we will be going over the code of how to implement the hand detection algorithm and to explain each and every step that we will be taking in the code. So as you can see from the screen, we will start off with this Python script which can be used to analyze hand gestures by contour detection and convex hull of palm region using OpenCV, a library used for computer vision processes. So first, we import all the essential packages to work with and initialize the model. So in case you don't have these packages installed in your computer, you should follow the previous videos where I have explained how to install these packages. So coming to the next part, here we are opening a video capture channel to the webcam. So here cap will hold the pointer to the webcam, and we are starting a loop here where we are saying that as long as the video camera is open, we need to execute the code that is there inside this loop. So coming to the first part, we will read the frame that is given by the webcam. So this frame will be stored in this image variable. So next we take a sub screen or sub window on the screen. So we will not be detecting hand from the entire screen or the entire video. So we will define a subscreen, that is 300, 300 and 100, 100. So this is a rectangle inside which if a hand appears we will detect it, and then we will crop the image to that rectangle, and then we convert this image into grayscale. So why are we converting this into grayscale? So our ROI, or the region of interest, is the hand region. So we capture the images of the hand and convert them to grayscale. Now you might be asking the question, why are we converting it to a grayscale? So the answer to that question is that we convert an image from RGB to grayscale and then to binary in order to find the ROI, that is the region of interest. So the portion of the image that we are further interested for image processing. By doing this, our decision becomes binary. Yes, the pixel is of interest, or no, the pixel is not of interest. As you might have already seen if you have gone through my previous video, that this is very important for contour extraction. So for contour extraction, we need to have a black and white image in which the contours or the object of the contours that we are interested in extracting should be of white and everything else should be black. So if we have an RGB image, it becomes very difficult for us to get this binary image. Therefore, we convert it into a grayscale image so that it becomes very easy for us to do this decision of subtracting the foreground from the background. So that is what we are doing here in the conversion to grayscale. And then we will be blurring the image. So here I've used the Gaussian blurring on the original image. So why do we blur this image? So like I said, even two identical images might have different thresholding or different changes in the absolute difference. So like we saw in the previous project, that is motion detection, we saw that if we do not apply blurring, then the absolute difference between two subsequent images, even though they look identical, can be very high. Therefore, we apply Gaussian blurring on the original image. We blur the image for smoothing and to reduce noise and details from the image. We are not interested in the details of the image, but in the shape of the object to track. By blurring, we create smooth transition from one color to another and reduce the edge content. We use thresholding for image segmentation to create binary images from grayscale images. So as it might be apparent to you by now why we are using blurring. So if we don't use blur, then in the image there will be sharp edges. So for example, if you take the image of a hand, and there will be a sharp edge between the hand itself and its background. Now even if this hand moves by 1 pixel to the left or to the right, then we will lose all the information regarding how that hand looks like. Therefore, we need to eliminate this edge effect where there are sharp edges between the objects, so that we can have a smooth transition between the edge and the surrounding images. So if we do this, we will be able to consistently extract the shape of the object instead of worrying about the exact edge and the pixel at which that edge occurs. So that is why we do the Gaussian blurring. Then we do the thresholding. So what is this thresholding? In very basic terms, thresholding is like a low pass filter by allowing only particular color ranges to be highlighted as white, while the other colors are suppressed by showing them as black. So I have used Otsou's binarization method. In this method, OpenCV automatically calculates and approximates the threshold value of a bimodal image from its image histogram. But for optimal results, we will need a clear background in front of the webcam, which sometimes may not be possible. So like we discussed in the theory part of this project, we saw that we need to do thresholding in order to mask all the background images with black and all the foreground images with white. So how do we do this thresholding? OpenCV gives us a very easy interface to do thresholding using something called as Otsou's binarization. So what exactly is Otsou's binarization? So in not-source binarization, we assume that the image consists mainly of two colors. One is the background color and the other is the foreground color. So what not-source binarization does is it models the background color and the foreground color and creates a histogram of all the colors available in this image. So when I say color, it is a misnomer because, like I said, we are dealing with the grayscale images. So even in the grayscale images, there are colors, right? So there will be very light gray and a very dark gray, and all the spectrum of grays are available even in the grayscale image. So when I say color, even though I am talking about a grayscale image, it applies to all the colors in the grayscale spectrum. So what not-source binarization does is it draws a histogram of all the colors available in the current image. Once it draws this histogram, what it does is it is a bimodal image. It assumes that the image is a bimodal image. So what do you mean by a bimodal image? That means there are two peaks in this histogram of the image. So we are assuming that the image will have two peaks, and then this peak will be split along with a certain axis. So what not-source binarization does is anything that is closer to one peak is given as white, and anything closer to the other peak is assigned a 0 value. Therefore, we are taking not-source binarization and using that to threshold our images. So coming to the next part, we can see that thresholded image when we run the demo. So let us find out actually the CV2 version that we will be using in order to avoid unpacking error. So what is unpacking error? So CV2 has different function signatures when it comes to find contours function depending on the version of OpenCV. Therefore, here we are checking if the version is 3 or 4, and then we are using the appropriate find contours function. So in our case, if you have followed our course from the beginning, you might have seen that our OpenCV version will be a 4. Therefore, we will be using this. So coming to the next part of the process, we have to actually extract the contours. So here we are extracting all the contours from 5 contours, and then we are finding the contour with the maximum area. So in the image we might find multiple foreground objects from the background, but out of all the foreground objects we are interested only in the maximum foreground object or the biggest foreground object. So in order to find the biggest foreground object, we will be calculating the area of each contour and finding the contour that has the maximum area. Now how do we actually calculate the contour area is by this function called as contour area. So till here we have theoretically covered all the concepts that we have been exploring in the previous videos. Now let us go over them one by one, including the function signature and the values, in order to truly understand what the code is doing. So first we capture the webcam because it is 0, it is webcam. If you want to read a video file, then give the path to the video file here. Then we open the stream to the webcam, and then we actually read the frame. And then we draw a subset of the rectangle, that is x, y values, that is 100 to 300 and 100 to 300, and we are assuming that we are only going to do hand detection here. So converting to grayscale, we know that it is in CVT color, and we say that read it in CVT and convert it from BGR to gray. So using this option converts this image from BGR to gray. BGR is just another form of RGB. So here we are converting BGR to gray. Here we are applying a Gaussian blur of value 35, 35. That means we are taking a square of height 35 and width 35 and 35 pixels, and we are blurring them. So we use the Gaussian blur function on the gray frame of value which is 35, 35. And then we do the not-source binarization, where we say, okay, threshold this blurred image with the value 127. So all the pixel densities that are greater than 127 is assigned a value of 1, and all the pixels that are of lesser pixel density than 127 is assigned the value of 0. And here we are saying that use threshold binary inverse, that is we are using a binary threshold and we are using an also binarization. Here I am sure we'll just show the thresholded image. Here we are checking the version of CV2, and here we are calling the find contours with a copy of the thresholded image because we do not want to mess about with the original thresholded image. And then we are also passing other functions, other options to the same function. And then here what we are doing is we are finding the max of the contours in which the max is calculated on the contour area. So here we are passing the key as the contour area. Alright, so now that we have got the final contour, that is the biggest contour, we are pretty sure that this biggest contour will have the hand region inside it. So next we will create a bounding rectangle around the contour. So what this does is we are just drawing a rectangle around this biggest contour that we found. So here we are saying cv2.rectangle of a cropped image and the x and y coordinates that we got from the bounding rectangle. And since this is BGR, we are saying 00255, so that means the rectangle will be in red color. Next we find the convex hull. So what we do in convex hull is we get the biggest convex hull from the contours. After that we actually draw the contours. So these two lines, we use the draw contours functionality in order to actually draw the contour around the hand. And in the next line here what we do is we find the convex hull and we find the convexity defects, and then we draw the contours on these defects. So we apply the cosine rule to find the angle for all defects, that means fingers. So till now we detected the hand, and from this step onwards we will be detecting the fingers themselves. So in the next video I will be going over this next part of the code in which we are actually trying to track the fingers and recognize the gestures. Hello everyone and welcome to Updegree. This is Sujay, your instructor for the OpenCV practical course. In the previous video, I explained to you about the code in order to extract the hand region. In this video, I will be going over the next part of the code in which we will be trying to extract the fingers themselves and track the gesture. So we already saw that we are extracting the convex hull, and then we find out the defectives in the convex hull. So the assumption here is that in the convex hull, any defect is because of the fingers. Therefore, if we find out what are the defects in the convexity, then we can find out where are the fingers present. So what we do is we get all the defects and then we count the number of defects using the for loop. So here we draw contours on all the contours, and then for each and every defect what we do is we find out the start, end and far regions of the defect. So then we find the length of all the sides of the triangle of this particular defect with this ABC. Now we find the cosine rule here in order to find out the angle. So any angle greater than 90 and highlight the rest with red dots. So we will be highlighting the fingertips with red dots. If the angle is less than 90, that means we are counting the number of defects and we draw a circle on that point. So the assumption here is that if the angle is lesser than 90 degrees, then that means it is a finger, because if we look at the fingers and the angle between them, there is no angle where a finger is greater than 90 degrees from each other. Therefore, we can safely assume that if we get an angle that is greater than 90 degrees, then that means it is not a finger point. So then we draw a line from the start to end, that is the convex points. So these convex points are the fingertips. So after this we define the actions that are required. So what we do is we count the number of fingers. Here we are counting the number of fingers to be 1, 2, 3, 4. So if we count this, we can safely say that we have detected one finger. So here we can change this text here saying that this means that we could detect one finger, and similarly if the count defect is 2, that means that we could detect 2 fingers. and if it is 3, it means that we could detect 3 fingers. And if it is 4, it means that we could detect 4 fingers. If it is anything greater than that, that means this means an entire hand. So what we are doing here is we are putting the text. So cv2.putText, we are putting the text at this coordinate in the image. So here we have different if conditions, where if the count defects is 1, that means it's 1 finger. If the count defects is 2, that means it's 2 fingers, and so on and so forth. Now coming to the last part, we will be showing the appropriate image, and all the images will be showed as a H stack, and then we will be showing it as contours. So here we are saying we will be taking in the input till we press an escape key. So 27 is the escape key. As soon as we press the escape key, then it means that we are done with the stream and that we can stop the stream. So this is the end of this video, and now that I have explained the entire code to you, in the next video we will be running this code and doing a demo of it. Thank you and see you in the next video. Hello everyone, welcome to Updegree. This is Sujay, your instructor for the Opencv practical course. In this video, we will be running the code that I explained in the previous video and finding out how it works. So you can save this code as gesture recognition.py in the same folder that we have been putting our codes. So here you can see in the terminal that so here I have saved it as gesture_recognition.py. So please activate your virtual environment like how I showed in the previous videos. So now let us actually go ahead and run the file. So I have run the file and I will be sharing my screen now in order to see how it looks like. So here you can see that this part is the subset of the entire video that we will be detecting the hand in, and as soon as I bring my hand in that, we can detect it. As you can see in the text behind that, we can see that it is a hand. So if you can see in the contours window, we can see the defects or the number of fingers that we are able to detect. If you can see the thresholded window, we can see that everything other than the hand is given as 0 and the hand is assigned the value of 1. So that is because of the odd-source binarization. And in the contours, the red is the biggest contour and the green lines are the ones that take the convex defects and count the number of fingers. Alright, so now that we have come to the end of the hand detection project, see you in the next video where I will be doing the next project. Thank you for watching.